the first thing which I'm going to do is to solve the homework problems, and then we'll continue, right? So the homework problems were, the first one was you were given a force field, two versions of it, and one of them is that F, well, it's force A. Its X component as function of X and Y equals minus 6X minus Y cosine XY and minus 14, this is 4XY, and the Y component of it, of the same force as function of X and Y, equals minus 5 minus X cosine XY minus 7X squared, right? And the B version of it, the only difference is that instead of that 14 here, it was 12, right?
Yeah.
Is it the problem you solved? Okay, good. So as usual, well, you've been in the educational system long enough. You know that if I give you two forces, then one of them will be conservative and the other will not, right? I mean, otherwise, why would I give two? So one of those forces must be conservative, the other is not. And in order to check it, the only thing which you need to do is to take the derivatives, dfx with respect to y and dfy with respect to x, right? And if those two derivatives are the same, then it is a conservative force. If it's not the same, then it is not conservative. So all we need to do is just differentiate. So you take the x force, the x component of the force, and differentiate with respect to y. This term does not depend on y, so it gives 0. This one gives you minus cosine xy, right? Then it goes plus xy sine xy, right? And this one I differentiate with respect to y, so it gives me minus 14x. When you take this derivative, you treat x as a constant and just take the derivative of the function which you have. Now the next one is you need to take the y component of the force and differentiate it with respect to x. So that will give me 0. This one will give me minus cosine xy. Here's plus. Then I need to differentiate with respect to x. So I differentiate with respect to this one. This is xy. This is plus again. Sine xy, right? And now I need to differentiate this one with respect to x. And what I have is minus 14x. Okay? So I look at them and I see that they are exactly the same. Those two functions are exactly the same. So for the first force, when I have 14 here, then it is a conservative force, and that's it. That's a proof of it. But now I see that if I have 12 here, that instead of 14 here, I'll have 12, and I still have 14. So the next, the B force, then will not be conservative, because then I would have 12 here, right? And this one is still 14 because I was differentiating this part. So they would not match those two derivatives, and it means that it's not a conservative force, right? That makes sense?
Yeah.
All right. Okay. Now the next question was to find out what is function u. If you have a conservative force, and now we need to only consider only conservative force, then there must exist some function u such that those two forces, as just this one is minus du over dx, must be equal to fx, and minus du over dy must be equal to fi. So such function u of x and y must exist. Now, in order to do that, the standard way to do that, well, there are two ways to solve this problem. One way is just to look at them and just to write function u, such that it has this property, and then prove that it is indeed so, just taking the derivative and finding that it's exactly the derivative of function u gives you this these expressions. This is perfectly, if you can guess, looking at those functions, you can guess the right answer, and you just write it and then prove that it's indeed those things are indeed satisfied, then that's a perfectly normal solution. There's nothing wrong with that. But it's if you cannot, if you don't have enough experience with those things, you may not be able to see the answer. Then what you do is the following. So here's your x and y coordinates. And remember that we always can choose one point to be zero potential. So naturally we choose this point, the x equals 0, y equals 0 to be our zero potential. And then function u at any other point, x and y. So here's my x, here's my y. Function u of x and y is exactly work which you need to do in order to move a particle from point 0, 0 to point x and y. That was the definition of potential energy to begin with. So we need to take our particle at this point and move it to point x and y along some path. And the statement is that the resulting work which we calculate does not depend on the path. So what it means is that we can choose whatever path we want. Right? So I'm going to choose the path which is this one. It goes first along this direction, along x direction, and then it goes along y direction. Right? So here's my path, and I want to compute the work which I need to do along this path. So how I do that? Well, I know that work equals integral f dot product with dr, and that's it, right? And so it's the potential energy is minus that work, right? It's defined with a minus sign. So then what do I have here? And I need to take this integral along some path. Here's my path. I need to split it on little pieces and compute for each little piece f times dr, and just sum them up. So that's exactly what I do. So first, what I notice is that my path has two distinct pieces. Right, so it's at the integral from 0 to x, this x, right? Now, when I do, so that will be the first piece, and the second piece will be integral when y changes from 0 to y. So my y will change from 0 to y. Now, inside there, I need to split now every for example, this segment of my path on little pieces. So here's my dr. Now I notice that dr has only x component, so it means that I need to write here f x component of force x. Right? Now, on everywhere here on this interval, my y coordinate is 0. So it is f of x prime 0 dx prime. Here's my first piece. And the second piece, again, this one, here I see that dr has only y component. So I need to consider only y component of the force because it's a dot product. Now, along this path, all x coordinates are just those x, right? So what I have here is x. Then I have y prime, dy prime. Here's those two integrals which I need to take. All right. So I proceed. I just now take my force f of x, which I know, x component of the force, which I know. I substitute there. Substituted here. There's a y component substitute here, and what I have is the following. I have now f of x. While y equals 0, so x component of force, and I need to plug y equals 0 here. So I plug y equals 0 here. I see that this is 0, this is 0, and the only thing which will be here is this one. So I have minus integral 6x prime dx, and I need to integrate it from 0 to x. This is this integral plus. Now I need to take y component of the force, substitute there everywhere instead of keep x in there and substitute y prime instead of y. So what I have here is integral minus 5. Then I have minus x cosine x y prime. Right, this is this one. Minus 7x squared. This one. And I need to integrate it over y prime, dy prime. Right? That makes sense? And the integral should go from 0 to y. So what I have now I take those integrals, and they're simple integrals. So this one is minus 3x squared, right? Then I have minus, then I have here 5y. Here I have minus sine xy, right? And here I have minus 7x squared y. That's all. Now, potential energy is defined with a minus sign, so the answer which I have is the following. I have u of x and y equals 3x squared plus 5y plus sine xy and plus 7x squared y. Right? That's all. Now, as usual, in this case, when you have some result like that, the next thing which you always should do, even if you are not asked explicitly to do that, is to check your answer. So in order to check your answer, what you need to do is to write that fx must be equal to minus du over dx, right? So what you need to do is to just take the derivative of that, well, with the minus sign. So what you have is minus 6x minus y cosine xy, and here we have minus 14xy. And you notice that it's exactly the same as expression here. And the next, of course, you also need to check fy, which is minus du of dy, and you now need to take this derivative with respect to y. So we have minus 5. Here we have minus x cosine xy, and here you have minus 7x squared. All right, and you compare it with what you have initially, and you see that it's all matches up. All right, that makes sense?
Yes. Yeah.
Now it would also be actually a very good exercise if you do it, that calculation of u with this path, and then you say that, well, it should not depend on the path, right? So you can now, what if I take this path? Will I have the same answer? The answer is yes, and you can do exactly the same calculation. So now along this path, so here you integrate over y, so it's only y is important, here you integrate over x, it's only x is important, and so fx is important, and so forth. So and you will get the answer which is exactly the same potential energy. And so this way you will actually see that it indeed does not depend on the path. If you're like very, I don't know, nerdy like myself, you would also can check some other path, like for example this one. This integral is well, you need to split it on components, dr on components, f on components, and write that dot product between them. It's again will be two separate integrals, and you take it, and you again will get exactly the same expression. All right. So it's it all works out. No matter how you do, no matter what path you choose, it will give the same answer. All right. But again, if you're very experienced with taking derivatives, you can just write this function just out of the blue, just say that, well, here's my answer. Now, but after that, if you do that, you have to provide a check that it is indeed so. Then it is a complete solution. If you just write this function and then just differentiate it and say, you see, I got what I needed. That's it. That's enough. It's as good as any other solution. It's up to you how to take integral. If you can do it in your head, then it's fine. So any questions?
Yes, I actually had a question
Sure.
real quick. So whenever we first established the integral for like fx and fy, and we added those integrals together, we got that from work, didn't we?
Yes. Yeah.
Okay, so how does that tie into finding the potential function? How do we go from work to the potential?
But it's a definition. The potential function was defined in such a way that it actually equals minus work, which needed to move the particle from one point to another.
Okay, that's what I wanted to make sure of.
It's actually a definition of potential energy. It's
Okay.
actually quite it's always good to actually have it in your mind when you're dealing with those functions. So, for example, I could never remember whether there is minus sign in front of potential for electrostatic force or not. And there's a lot of things which I cannot remember if my life depends on it. So what I usually do is then that I imagine that I have two charges, and then if they attract each other, then I have to do work to move it, and that gives me the sign of my potential energy, right? Or the other way, if they repel each other, then I have to do work. When that work which I do will be then completely. I apply this force and it goes this way, and I move this way, so the total work will be negative, and then from there I know that the potential should be positive. So I always have that picture in mind, and that connection between potential and work is work is a potential basically. The work which you need to do to move particle from one point to another is exactly the difference in potentials on this point, or the potential energy, if you want. All right. So it's something which should always be in mind, and that's what it is. Those things are not coming out of magic. They came exactly from the definitions of what you can do with your system. Right. Any other questions? All right, then let's move on and for the next problem. So the next problem was just a simple exercise to basically repeat the calculation of what I've done on the lecture, and now with a specific potential energy, and that potential energy now U now is given by minus x ma. M is the mass, A is just a constant, and x is our coordinate. It's one-dimensional motion. So again, what you can do is to write the energy conservation law. So m over 2 dx over dt, which is velocity, right, squared, plus u, which is minus x ma, equals the total energy. Right, that's my energy conservation law. Now, the total energy, if I have some initial positions, so my initial position x naught and my initial velocity v naught, then the energy equals initial kinetic energy minus, plus initial potential energy. Right? So that's my E. If I have some initial conditions at t equals 0, then this is that's the energy, and energy is conserved, so it's the same number here. So what I do after that, let me do the blackboard tricks here. So I first move my potential energy to the right hand side, m a x, right, and then I just take the square root of this, and I have m over 2 square root dx over dt equals equals square root of e plus m a x. And the next thing, I just move that dt up here and all that square root down there, and I have m over 2 square root dx divided by e plus m a x square root equals dt. Now, in this form of the equation, what I have is all x is on the left-hand side, all time on the right-hand side. Right, so it's called the equation was factorizable. And so what I can do now is just to take the integrals of left and right hand side. So if differentials are the same, the integrals of the sum of those differentials must also be the same, right? Remember that integral is just a summation. So what I have now is m over 2 integral from x naught, right? I start from my initial condition to some other coordinate x, and here I have dx prime divided by e plus m a x prime square root, and it must be equal to the integral of dt. Integral of dt from t equals 0 to t is actually t, right? So what I have here is just, and all I need to do now is to take this integral. This is a simple integral because it's a square root of a linear function, and you can all, sorry, there is square root here. And so you can always take this integral either by mathematical or by hand. So if you decide to do it by hand, then what you have is the following: that you have m over 2 square root, and then integral of 1 over square root is a square root. So what you have is 1 divided by ma. Then you have factor of 2 here. Then you have square root of e plus m a x prime, and you need to take it between x naught and x, and it must be equal to t. Right? So that's your that's the integration, and this is the simple part. The rest of that is just simple algebra, which is actually the hardest part in this problem. So what I need to do now is I need to substitute those boundary values inside this integral and subtract one from another. Well, it's the standard thing which I need to do. So let me write it this way. So this is time, and then what I have here is 1 over a, and here I have square root of 2 divided by m, and here I have square root of e minus plus m a x minus square root of e plus m a x naught. Right? Remember that what I need to find is this x. So I need to do some algebra with all this stuff, and to find that x as function of time. So I need to sort of invert this function. Well, it looks horrible this way, but let's simplify things a little. So let's first use in this expression, let's use our e. So what we will have then is you can see that e plus m a x naught, right? It just means that I take this x naught ma and move it on the left hand side. What I have here is the square root of m v naught squared over 2. Right? That makes sense?
Yeah.
All right. Now you see that here's 2 over m, here's m over 2. They cancel each other. So what I have now is, when I open the brackets, is 1 over a times v naught. Right? Because it was v naught squared, I take square root, it's v naught. All right. So now on this equation, first of all, I multiply everything by a. Then I move this to the left-hand side, and what I'll get is the following: that v naught plus at equals, and the rest of that, 2 divided by m square root e plus m a x square root. Right? Now it's just simple algebra. It really doesn't matter how you do that. It it's up to you. I'm just trying to show you that it's actually doable. Now I still need to take this x. I notice that if I now take the square of both sides, then it actually gives me just x, pristine x. So what I need to do then is to say that e plus max times 2 divided by m must be equal to the v naught plus at squared. Right? That's my expression now. Okay, so let me move this m over 2 on the other side. It was 2m, so it's m over 2 here. Now I need to open these brackets, and what I have is m v naught squared over 2, not surprisingly, plus m v naught at. This is cross term, and plus m over 2 a squared t squared. Right? So here's my, then let me forget about the middle, and this is my equation now for x. Now it's just a linear equation. I can do it. So what I have now is that I need to cancel. I can forget about the middle part of it, and right here this way. So I just move e to the other side. Okay. And what I see here is that now I'm looking at this, and I'm looking at my definition of e, right? And I see that this is nothing but the whole term is just x naught ma, right? And now I see that I can cancel ma out. And what I have from here is x equals x naught plus v naught t plus a t squared over 2. Okay? That makes sense? So I ran through that very fast. I know that. And because I don't have much time to spend on those things. But what I'm trying to emphasize is it's just a simple algebra. You just do it. That's it. I mean, algebra is a work, so it doesn't. And so you take it and you work on it. And if it works, you got the answer. If it doesn't, then you do something else. And so, but what the point was though to show you that this expression, that your standard expression, which you probably remember, it also comes from the, it can be derived from the very same procedure which we described last lecture, right? So I showed you back then that for any one-dimensional system, for any conservative force, I can solve this equation, and that was a part of, and that solution was here. But it's always good thing when we have some general statement to check whether it works on in the situation when we already know the answer. So we already knew this answer. So I wanted you to check that whole procedure of one-dimensional motion with conservative forces actually works in the case which you know. All right. So that's any questions on that? All right. Then let's move to the next problem. This is problem number 3. And the problem number 3 is the following: that you have some potential energy. Again, it's one-dimensional motion. You have potential energy U, which is k x to the force, right? And you need to find the period of motion in this potential. And k is positive. So the first thing you should do in this equation is first to draw that function u of x, right? So this expression will look something like this. Now remember that if you have some, if your initial energy is some constant, I don't know, it doesn't look like constant to me. Here, all right, now it's constant. So this is x and this is u. So So what I see is that there are two turning points. But also this u is symmetric with respect to change x to minus x. So if this point is x naught, then this point is minus x naught. Right? Then I know that the period x for any such motion between two turning points, right? And so the motion will be from one turning point to another and then back, and then keep going. So the period is 2m divided by 2 square root integral from minus x naught to plus x naught, and here I have the x divided by e minus k x to the fourth square root. So that's my period, right? Now all we need to do is to take this integral and see how this integral depends on e. But reality, you don't need to take this integral. All we need to do here is to make the substitution. Say that x equals e divided by k in power of 1/4 times y. That will be my substitution, right? Now, before I do the substitution, when I do the substitution, right, I need to substitute it here, and I also need to rewrite what my upper and lower boundaries are in my new variables. Right. So what I need to do is to find what that x naught is. So x naught is exactly where E energy equals my potential energy, right? So E must be, that's the equation for x naught. So this is the equation for x naught, right? Where E equals potential energy at the point x naught. So from here I see that my x naught equals E divided by k, and I need to take 1/4 out of it. Oh, yeah, right? Oh. So now, if I look at this and I substitute that x naught here, what I find is that here is E divided by k 1/4, and it will be cancelled by this one. So my integrations then u naught equals 1, right? So when y equals 1, my x equals exactly x naught. So what I have now after the substitution, I will have, let me write it somewhere here. So what I have here is 2m divided by 2 square root, and then I have integral from -1 to 1. And now instead of the x, I need to substitute the differential of this one. So it's e divided by k in power 1/4 dy. And now I need to substitute it here. So I have e minus, and instead of x, I need to substitute y. So when I take the force power of x, I will have e divided by k. K will cancel this one, so I have e y to the 4th square. Right? And now I see that I actually can pull energy out of this integral. And what I have is 2m divided by 2 square root, and then I have e divided by k in power of 1/4. And then I have 1 over square root of e here. Or let me write it e to the power 1/2. 1 over e in the power of 1/2. And the rest of that will be just a number. It's integral from -1 to 1 of dy divided by 1 minus y in the 4th power and square root. Right? This integral now depends on nothing. It's just a number. So, but the question was how the period depends on energy. So looking at this, what I can see is that I have e in -1/2 power here. I have e in 1/4 power here. So what the answer then is that the period depends on energy as it's proportional to energy in -1/4, right? Because it's e to 1/4 divided by e to 1/2. It's e to -1. And so this is the answer. You can see that when energy is growing, then because that's negative power, when energy is growing, then the period becomes smaller. Okay, and you know how, right? It's you very specifically know how it will do it. So you can actually plot the functions and see if it's indeed so. You can also from here you can also calculate the coefficient in front of here. It will be some combination of k, m, and there is some number which you can either compute numerically or you can ask mathematically what this number is. It's up to you. Right? Any questions?
That makes sense. Thank you.
All right. So the next question was what will happen if I have 2 here instead of 4, right? And then what you know, so let's instead, well, I'm usually lazy, so, well, not usually, always. So instead of like solving like different kind of problems with different those powers here, let me solve all of them and just write here absolute value, and here's alpha, right? And then I'm just looking at my solution, and what I see that here will be alpha, right? And then looking at this, what I will have, I need to make the same substitution, but it's not 1/4, but 1/alpha here, right? And according to the rest of that, the rest of that will just go through exactly as it is. And I remember that one of the powers of E come. So one of them will be this one, E in 1/alpha, and the other power is coming from that. Remember that when I pulled E out of the square root, so it's minus 1/2. Right. So that's the answer for any alpha here. It just is exactly the same calculation, but I just know where those factors of E come from, so I can see where they come from when it is alpha. So here is E in power of 1/alpha, and 1 more square root is coming from downstairs. That makes sense? So from here you immediately can see that if alpha is larger than 2, then alpha is larger than 2, then this is negative, and it means that period is growing, period is decreasing when E is increasing with energy, right? So T is increasing with energy. No, decreasing with energy. So decreasing with energy, and when alpha equals to what I have here is 1/2 minus 1/2, right? Which is 0. E in power of 0 is 1. So the T does not depend on energy, and it's just a constant. Right? And this is your oscillator. And when alpha is less than 2, then what I have is that the period will be actually increasing when with energy. Right? Because then when alpha is less than 2, then 1/alpha is more than 1/2. So this is a positive number, and if I increase E, it will increase my period. So here is the answer which you were supposed to figure out, and but you see that just sticking here some alpha, you can actually learn a little bit more. Now it's actually quite an interesting story of think about why it is so, why alpha equal 2 is so special. And then you look here, and you see that period depends on energy in the power of which is 1/alpha minus 1/2. So this is 1/alpha is exactly coming from here, from the potential energy. So the question is, where is it 1/2 came from? And that came from the square root. Remember that from this square root. Now, where is that square root came from? It came from the fact that you have that your potential energy, that your total energy equals mv squared over 2 plus u, right? So remember that what we did, we take u, pull it here, and then took the square root of follow that. That's the square root which is here. That square root we have taken because there is factor of 2. There is power of 2. Velocity is in power of 2. So this square root is a reflection of our dispersion relation. It's how kinetic energy depends on velocity or depends on momentum and so forth. So that square root that 1/2 is coming here because of that 2 here, right? And then what you see is that if alpha equals 2 in potential energy, then what you have here is kx squared, right? So we see that when this equals to this, then period does not depend on energy, and that's the origin of it, because when both of them are the same power, you have additional symmetry in the problem. All right, so that actually leads to a lot of different consideration. That it's especially in quantum mechanics that symmetry is very manifest and very much, and it tells you that the oscillator is something special, and you can and actually exactly due to that symmetry we actually can solve oscillator problem in quantum mechanics, because in quantum mechanics really there's only 2 problems which you can solve exactly. And the rest of them we have to do some tricks. Any questions so far? All right. Okay. So the next question there in the problem was what if that k is negative? And if k is negative, then again you just draw that function u as function of x when k is negative. So it's let's say alpha is 2 or 4, but then what you notice is that it will look like this. All right, so if you have now any energy, it's either this, so if any total energy is negative, then it's the only allowed space for you is either this one or this one, and it means that there is no stop. There is only one stopping point. There is the other stopping point at infinity. So whatever you do, then if you put particle here, it will just shoot to the infinity and never returns back. So the motion will not be periodic in this case, and that's exactly the statement of when k is negative. Or you can actually think about it on the following things: that if k is positive, right, and then you have something like that, the energy. Then if you start close to 0, it will always sort of be close to 0. It will be oscillating back and forth, but it will never go away too much. And if your initial energy was small, then it will oscillate very, very close to 0. It never go away too far, right? And that sort of stability, right? It means that if you put particles there, it stays there. It oscillates, but it still stays there, and at least you know approximately where it is. But in the situation when k is negative, then what you have is a completely unstable problem, because you put particle somewhere and it just shoots to infinity, and you'll never find it again. So it's unstable. What we call it is unstable situation. Okay, does it make sense? We'll discuss those stabilities a little bit later also. All right, so that's it for homework. Any questions? Come on, guys. It's very boring here. Any questions?
So for that last part, when k is less than 0, it just keeps going towards infinity?
Yeah.
Okay.
Yeah, that's it. Now, I mean, now it depends on what you solve it, right? If you solve the problem which is given to you by a professor or whatever, teacher, then yes, it just goes to infinity. But if you're trying to do something reality, right? So something which some real problem, real world problem, whatever it means, there is no infinite distances, right? What it means is that you only know that potential energy typically around some point, around 0. But here, very, very far away, there can be another potential well, right? And the particle can get trapped there. And that's entirely possible. and it means that it doesn't go to infinity. It will just go to another minimum of potential energy. But again, we will discuss that a little like probably next or the lecture after next in a little bit more details. All right, it's so, but for just the problem as it's stated, that's it. It just goes to infinity. It doesn't matter really how where the initial velocity is directed. If the initial velocity is towards infinity, then it just goes to infinity and that's it. If the initial velocity towards the center, then the particle just comes here, hits the turning point, and turns around, and again goes to infinity. And there is nothing else. It's just shoots out. All right. Did I answer your question?
Yes, thank you.
All right. Okay. Now that was homework, and let's now proceed with our material. So if you remember last lecture, I was talking about functionals as a map from space of functions to numbers. And at the end, I asked you to think about any functional which you have in real life. Have you done it? Any examples? Come on, guys. Anyone? You see that when I ask, have you done that? There are only two answers possible: yes or no. Right? Both are fine. I'm not going to grade you. I will not even know your names if you answer it. So please answer me when I ask questions. So have you done that? Have you thought about it?
No. Well, I've thought about it, but I haven't come up with an answer.
All right. Well, thinking is already good. Well, I hope you had some. All of you had some sort of ideas that you need to think about it, and probably try to think about it. But in reality, the question is very simple, and in a sense that everything which you do is actually functional. Well, think about it. You have money on your account, and you do something with that, right? So you spend it, you earn some more, you spend some more, you earn some more. So it's a process, right? So the total money on your account depends on time, right?
Yes.
But let's imagine that you're only interested at the final value, like in 1 year, how much money you gain or how much money you lost during the year, right? So you have then that process which you do, like you sell something, you buy something like stocks, for example, right? And at the end, you see if you did better than you started from, or worse than started from, or you just did it all for fun, and you are exactly where you've been before. But that's exactly the functional, right? You do something, it's a function of time, but you are interested only in the final number. So you have some bunch of functions, and for each of those functions you have final number, whether your wealth increased or decreased or stays the same, how much it increased. So that's a functional, and now you can ask yourself, what should I do in order to increase the final number? What kind of path? What do I need to do with my money in order to increase the final outcome? Right? Perfect question. I wish I knew. And the answer. And so that's a functional. Now let's imagine that you are traveling from here to Houston, wherever you want to travel through, and you can take multiple roads to there, and each road has its own speed limit, and you never go over speed limit, of course, I know that. And so the time of arrival, or how much time it takes for you to go there, depends on which route you take, right? To Houston. So again,
yes.
that route. Say again?
Said yes.
Yeah, all right, good. So that route is your function, right? Which roads you take, and you can draw it on the map if you want. And the time of arrival, or the time of it takes, is just a number. So you have correspondence between what you do and the final number, and that's a functional. So if you think about it this way, that it's exactly everything which you do, in fact, you can be cast in a function. it's actually more general than you think it is. It's actually moreover, it's actually more general than the functions themselves. Because after all, when you go from here to Houston, the only thing which you're interested in is how much time it takes. I mean, unless you want to have some scenery and stuff like that. There are much more complicated questions of the same kind. Let's imagine that you have a bunch of merchandise and you need to sell it in different places, and those different places are connected with different routes, and you need to find out which route will take you, which will go you through all the places you need to visit, but you need to do it such a way so that you spend as little time or as little gas, if you want money, on the travel, right? And then what you need to find is the one route which satisfies your requirement of minimum length, of minimum cost, right? And so that's another functional, and it's actually quite a relevant problem. And it's if you think about it, that's exactly what, I don't know, UPS or Amazon are doing. And the funny thing is that that's one of the most hardest problem in which we know, and there is no way to solve it generally. And but you still can do like some sort of optimizations, right? Does it make sense?
Yes, that makes sense.
Now, I want you to point out your attention to something which is common in all those things which I described, all those functionals which I described, that we really don't care much about the functional itself. What we do care about is to find such a function, such a route, which gives us the minimum of a functional, right? So the functional is a number, right? The value of the functional is a number. So those numbers we can compare. We cannot compare functions. You cannot say that one function is bigger than the other, because what does that mean? But we can compare numbers. We can say always that one number is larger than the other, or equal or smaller or less than the other. So then what we can do is to ask the following question: which route from here to Houston we should take in order to minimize the time of travel? Now, the time of travel is a number. The route is a function. So which function which we need to take in order to minimize the functional, right?
Yeah.
The same is money, right? What I need to do with the money on my account, that's a function of time, right? I sell, right? But it's a function. And what do I need to do in order to maximize the final outcome? Usually that's what people want to know, right? Or is that travel salesman problem? What kind of route do I need to take given the map and all that constraints, conditions there, in order to minimize the money which I need to pay for it, right? To minimize the cost of delivery of the goods, right? So that's, again, you have a functional, but you actually you have a functional, right? Some s as some functions of f of, I don't know, time or x, whatever your coordinates are, and you need to find. And remember that this is a number. This is a function, but the functional is for each function gives you a number, right? So you want to find such a function that this number is a minimum or maximum. That's a typical problem which you have, right? That makes sense?
Yes.
So that's a typical problem for functionals is nothing but just to find what function provides you with the minimum, or what function provides you with the maximum. But it's the same problem. You just need to take 1 over functional, or minus, put a minus in front of it, whatever you prefer. And so the typical problem which you have is you have a functional, and remember each functional is given by each function which we are interested in. Not every functional. There are different kinds of them. But the functionals which we are interested in are given by function of 2 variables, right? Those are 2 numbers which I can stick in here in those places, and then I will have a number, right? 2 numbers. One gives 2 numbers, and then they give me 1 number. It's a function. And then if I give you some function f of x, then the value of the functional on this function is given by s of f of x equals integral of L, and then in the first argument I stick f prime of x, and the second argument I stick f of x, and then I integrate it over the x. And I need to know from where to where I go from here.
Could you explain what you're doing again? I don't understand where S came from and what you're trying to do here.
Yeah, okay. So I want to. So the story is the following. Let's imagine that I want to go from point A to point B. All right, and I can do it different ways. This one, on this one, and so forth, right? And each of those ways are described by sort of a function, right? So if this is my y, this is my x, and let's imagine so each of those paths are described by y as function of x. Okay, that makes sense?
Okay.
So far, all right. And now remember, imagine that I want to find a path which has the shortest distance going from A to B, and that's exactly something which we discussed before. Then what do? I need to compute the length of the path for each of those functions. So I say that length of the path, let's call s of y of x, right, equals some integral, right? And it's 1 minus y prime square of dx. That's what we derived before. And I need to go from point A to point B. So it's from point A, from xa to xb. Okay. So that's exactly what I'm doing here. I say that let's imagine that we have some functional. And as was discussed last lecture, every functional which we're interested in will be given by a function. So if I give you that function L of 2 arguments, then it uniquely defines the functional. And it defines it by the following procedure. That functional s of f of x, right? So what's the functional? I give you function f of x, and it returns me a number. Now, by some rule, there is a rule which for every function gives me a number. Now I need to specify that rule in order to specify the functional. So it is specified by this single function of 2 arguments by the following way. I take this function of 2 arguments. In the first argument, I stick f prime of x. So I give you function f of x. You take it. You take the function L. You stick the derivative of x in the first argument. You stick the function f of x on the second argument. Now you have a function of only x, and then you take the integral from some boundaries, which also should be defined, right? And if you do that for any function, I give you f. I give you a function, and you know function L, right? I give you a function, you know function L. You do this construction. That construction, that thing will return you back a number. Right?
Okay.
Yeah.
And that number is the value of the functional on the function f. So you remember that what we do? We say that there are a bunch of functions, y of x, and for each of those functions, for each of those paths, we need to be able to assign some number, let's say time or length or whatever it is, or money. I don't care, right? So each of those, let's say that we have some functional, and for this function, it gives me 10, the value. Like if I do this, my money changed by 10. If I do this, my money changed by minus 12, right? So each of those paths gets assigned a number. That's a functional. Now we need to define how we define those functions, how we compute them. And one way to do that is to say that there is some special function which depends on what we want to compute. Right? It's function of, say, 2 variables. And so we take the function, the path, arbitrary path, but we know that, right? It's any path. We stick it in here. this way. We take the integral, and that's exactly the value of our functional. That's how we define the function. Let me give you an example again. The same thing actually. Let me say that I want to go from point A to point B by the shortest possible distance. So I have all the paths which I want, which I can take. All the paths are given by function y of x. And then I know that the length of this equals integral 1 minus y prime squared square root dx. Right? And I need to go from xa to xb. Right? This is my length now, right? Let me use another letter. It's a calligraphic error. All right. So now look at this. That has exactly the same form of this one, right? So my function L here, which was a function of 2 arguments, it turns out that it does not depend on the second argument at all. But the function of first argument, let me call it, I don't know, z1 and z2. So it's 2 arguments. So if I take that function equal to square root of z1 squared minus 1, no, the other way, sorry. 1 minus, what is minus here? Plus. Sorry. 1 plus z1 squared. So this is my function L as a function of 2 arguments, z1 and z2. Here is that function. Now, if I do this construction, I need to take this function, right? Instead of the first argument, z1, I need to substitute the derivative of my function f, right? And it doesn't depend on the second argument, so I forget about it. So what I will have is exactly this function, or the length. Right?
Yes.
That makes sense?
So I'm confused as to why the second argument doesn't matter in this case. That integral that you have drawn, is that just a general case for any functional that we're looking at?
Exactly, yes. This is general case which we want to consider. And this is one particular case where it just so happens that it doesn't depend on the second argument.
Okay, and so
yeah, just a second. I can make it differently. I can say that my velocity with which I can travel is different in different points, right? That's a typical situation when your highways have different speed limits. So it means that my velocity, let's say velocity is function of x and y, right? So in each point of that space, I can have only that much of velocity, right? Then what I need to do, like this is my dl, right? And now I'm interested not in the length of the path, but I'm interested in the time it takes me to go from one point to another. Then all I need to do is to say that time, now a function of y, will be divided, will be equal. I need to take this dl and divide it by velocity, right? Of x and y, right?
And so in that case, you would have a second parameter.
Yes, I actually have a third also. I have the third one, but I will not use those kind of things. So okay. Yes, then you see that my function L now is more complicated. It has z2 also, it has z3, and I have velocity divided by z2, z3, and so on. Right? That makes sense?
Yes.
So it's that's the length is the simplest example, but you can think about a lot of different examples. For example, that time of travel from point A to point B. But now remember that the only thing which we're interested in is to find out which function of f, gives me the minimum of this function. Or in this particular case, which path, y as function of x, right? It's my path. Which of those paths gives me the minimum time to go from point A to point B? Right? Does that sound reasonable? Question?
Yes.
That's what you always do when you go from point A to point B. Well, you're using Google Maps, I know, but that's what Google Maps doing. It tries to find the route which gives you the fastest, the smallest time of travel. Right? That makes sense? All right. So it turns out quite interestingly that this question can be answered. We can write a differential equation, such differential equation, solution of which will provide us with minimum of this function. So again, the function is defined by this function L, so we must know it. Otherwise, we don't know what we calculate. So we know this function L, and we need to find out the differential equation of function f of x, which we can solve, so with the conditions that if we solve it, that this function f of x will provide us with the minimum of this functional. So if you take any other function, not the solution of the differential equation, that will be maximum. That will not be minimum. It will take more time to travel. Right? So that's exactly what I'm going to do. It's find the minimum of such a functional, and I'm going to do it quite quickly because I really don't expect you to become an expert in those calculations. Simply because it usually takes about, I don't know, a third semester to teach students to do that. But I just want you to understand that it's doable. So what we have is the functional of function f of x, which is given by x integral from xa to xd, and then we have L, which is given function of f prime of x, the derivative of function f dx. Right, this is our function. Now we need to find such function f which provides us with the minimum of this function. So we need to consider all possible functions and find which one of them gives us the smallest number. Right? That's the idea. We need to take all the function f of x and compute that number for all of those functions and find out which function gives us the minimum of the minimal number. All right? That makes sense?
Yes.
So I want you to notice that everything is doable here. If you know this function, all you need to do is to take this function, stick it in there, and take the integral. That's it. So for each function, you'll have a number. And you can do it for all the functions, presumably. Well, you can't physically, but I mean, fundamentally you can. And then you have a list function number. You go through this list, find which is the smallest number in that list, and see which function provides you with that number, and that's the solution, right? So it's in principle that question makes sense. Now it doesn't necessarily have a minimum, but if it does, then you can do that trick and find it. As usual with the functions, right? It doesn't necessarily have a minimum. A function doesn't necessarily have a minimum. But if it does, then differentiating that function and saying that derivative equals 0, you find where the minimum is. This is exactly the same. You see that argument here is a function. I need to find the functional, right? So I need to find such a function which provides with the minimum. But that's exactly the same as with normal functions. With normal functions, just use the word function instead of functional. For any function, right? If I ask you where the minimum is, it means that you need to find such value of the argument. This is argument, this is function f of x, capital F. And you need to find such a value of the argument which gives you the minimum of the function. Now I'm asking you which value of the argument, but value of the argument now is a function. Which function gives you the minimum of the function? Okay? Does that make sense?
Yeah.
All right, so now what we do is we need apart from the big difference of that problem with the standard function is that the space of functions are too large. Is too large. So we need to restrict it somehow, and it's sort of natural restriction. It always comes naturally, in the sense that if you want to go from here to Houston, right? So your initial point and final points are fixed. So what we want to do is to consider only the functions such as f of xa equals fa, a given number, and f of xb, those xa and xb, equals fb. If you think about this as if you think about the travel from point A to point B, this is A, this is B, right? This is xa, and this is my f of xa, right? So then those xa, this and this are just my coordinates, and this are coordinates of the Houston. That's a place in Houston where I want to go. So I want to go from point A to point B. So that's why I fixed those boundary conditions, right? And now on space of the functions which satisfy those boundary conditions, you see, I'm giving you the example, and then I try to say the same thing, but in more abstractly. So I don't think about that Houston anymore. I hate that place. So in more abstract language, what it means is that I need to consider all the functions which satisfy those boundary conditions. The function at point xb equals some given number of fb, and the function of at point xa equals given number fa. And the space of that functions which satisfies the boundary conditions, I need to find such a function which provides me the minimum of my functional. Okay. So let's do that, and the calculation is actually very simple, but it may be somewhat unusual. So I try to first explain what I'm doing, and then just do it real quickly. So the story is the same as finding the minimum of a function. So what is the minimum of a function? We need to find such a place x naught, right, for the minimum function, that if we go either way, the value of the function is increasing, right?
Yes. Yeah.
But it means that if I now start from here and move this to the right, the value of the function must increase. And if I move it to the left, the value of the function also must increase, right? So if I say that the change of the value of the function, change of the value of the function, when I go a little bit to the left and a little bit to the right, right? So this is f of x plus delta x, x naught plus delta x, minus f of x naught, right? This is a change of the value of the function when I shift it a little bit to the right or to the left, depending on where my delta x is positive or negative, right? And either way, whether it's positive or negative, this must be positive, because the value of the function must increase, right? Does it make sense?
Yes.
But now if this function is regular, what it means is that it must start with delta x squared, and this what's in front should be positive, all right? Because if it starts with k delta x, the linear term in delta x, when delta x is positive, this is positive. When delta x is negative, this is negative. But if it is negative, it means that the value of my function decreases. But it cannot decrease because I am at the minimum. X naught is the point of the minimum. So it means that such term should disappear when I shift it a little bit. And only the second term should appear. But that's exactly the statement that the derivative must be equal to 0. Right? Because the derivative of it, if we just need to divide it by delta x, divided by delta x, divided by delta x, and then take delta x goes to 0. That's the derivative of the function f at point x naught. And but when I divide it by delta x, I will see here k delta x. If I now take the limit delta x goes to 0, this goes to 0. So it means the derivative equals to 0. That's exactly the statement of finding the minimum of a function. Right? That makes sense?
Yes.
So, then it means that I need to do exactly the same here. I need to think, okay, let me imagine that I found the function which provides me with the minimum of this function. I already solved the problem. Let's imagine that I know that, right? And it satisfies those boundary conditions. Now I say that let's imagine that I shifted that function a little bit. So if I have this function f of x, right, and I know that this is my minimum, that function provides my minimum. Then what I do, I say that let me consider a function which is very close here, this one, or this one, right? So this is my solution, and I need to consider the functions which are nearby. And no matter what is delta f is, right? If this is a minimum, no matter what delta f is, the value of my functional must increase. Right?
Yeah.
Because that's minimum. That provides me with the minimum. So that's exactly what I'm going to do. Now, in order to do that, I also notice that for delta f is a function, and it has the following boundary conditions. The delta f of xa must be equal 0, and delta f of xb must also be equal 0. Simply because this function already satisfies my boundary conditions. So in order this function to satisfy my boundary conditions, that function should vanish on boundaries. You see that all the functions starts from point A and end up at point B. That's important part for the computation and in general, but you'll probably miss where it's important. I'll point it out where is those things important. So what I need to do, I need to take this function and substitute instead of f, substitute this function. So let me do that. So then s on the function f naught plus delta f equals, let me write it. I don't have enough space for it. Okay, let me start writing here. It equals to integral from xa to xb, and then I just substitute here f naught of x prime plus delta f of x also prime f naught of x plus delta f of x dx. Right? That makes sense?
Yes.
The only thing which I did, I just took this and substituted here. Exactly what I'm supposed to do in order to find the value of the functional on this function. So then the next thing I look inside here, and I remember that this is a function, right? So this is a function, and I shifted its arguments just a little bit. Right. So when I shift the arguments just a little bit, I can use Taylor expansion or differential if you want to write the following thing: that this equals to integral from xa to xb, and then I have L f naught of x prime f naught of x naught plus, here I have this, then I have dl, and now I need to differentiate this L with respect to the first argument, df naught. This is just differentiating of the function with respect to the first argument times delta f naught, right? Prime here. First argument is prime, and plus dl over df naught delta f naught, right? And I need to integrate it over dx, right? That makes sense?
Yes.
Yeah, this is small, right? So all I need to do is just to take L, differentiate it with respect to first argument, and multiply by the shift of the first argument. Here it is. take L differentiated with the second argument multiplied by the shift of the second argument. That's all. I don't do much else. But now what I see here is that this is the value of the functional when I take the integral, right? On the function f naught. So what I then have here is that it equals to s, the value of the functional of the function f naught, plus whatever is staying here. Integral from xa to xb. And this is dl over df naught prime delta f prime plus dl over df naught delta f naught. Dx. Okay? Does that make sense?
Yes.
So the statement then that f naught is the minimum is such that no matter what delta f here is, no matter what delta f here is, that should not be negative. The whole integral should not be negative, right? So, but the problem here with analyzing it is that if delta f, here I have delta f, and here I have derivative of the delta f, all right? And in order to get rid of, and then I can, then those two things are not independent from each other. So in order to get rid of that problem, I'll do some standard, absolutely standard trick. I will take this part of the integral, and I write it the following way, that it's d delta f over dx, right? It's derivative. And then I do integration by parts. And if I do the integration by parts, what I will have here is the following, that it's minus d over dx, dl over df prime times delta f. And let me take delta f out. Okay. Now again, this all calculations are written on my lecture notes. Please, if you're interested in, it's you can read it there. But if you're not, it's okay. I mean, as I said, I'm not expecting you to be proficient here, so I don't want to spend time on explaining some details. Now, by the way, exactly on this integration by parts, those boundary conditions become important. But it's again, those are details which I really don't think you should be bothered about. So what now we have is that delta. You see that now the statement is that no matter what delta f is, this thing must not be negative, because that's exactly the change of the value of my functional. Right? Does that make sense?
Yes.
So I shift my delta f a little bit, and the value of the functional must increase. So this is the initial, the value of the functional on function f naught, and this is the change of the value of the functional. No matter what delta f is, this function, the whole thing must increase, right? So it means that it must be positive, or not negative, right? But it cannot be, because if for any function delta f, I can always, because remember that this is for any function delta f, it is so. So if, for example, I take delta f, I compute this integral, and it turns out positive, right? Then I take minus delta f and stick it instead of delta f, because the first one was positive, then this one will be negative, right? And that means that the value of my functional decreases. Does that make sense?
Yeah. Can you explain that again real quick?
All right, so this is the value of the functional on the function f naught. If I shift it a little bit, that function f naught, just a little bit, right? The value of the functional must increase, because f naught provides me with the minimum. I cannot go lower than minimum, right?
Yes.
So this is the value of the functional on the function f naught. When I change, when I shift delta f just a little bit, that's the change of the value of the function. So that change of the value of the functional must be positive. So that the functional is larger than the original one. Right?
Yes.
So now imagine that now let's see, is it possible at all? And so let's imagine that I choose some delta f, some function delta f of x. I stick it in here. I remember that I actually know what my function f naught is. Right, so I can now compute this integral for this particular function delta f. And what I get then is that this is, let's say that this is positive. So the value of the functional has increased. This is good, right? But then I take another delta f, which is original delta f with a minus sign. So I take minus delta f. And I stick it in here instead of delta f. Right? It must be positive for any delta f. So if I just change the sign of any particular delta f, it is still delta f. So I can stick it here, but then the value will be negative. And it means that the value of the functional decreased. Okay? The only way to avoid this is to demand that this is 0. Then no matter what I stick in here, I get 0. Right? So what it means is that my function f naught must satisfy the following differential equation. dl over dx prime. This is just a differentiation of f with respect to the first argument. Must be equal to dl over df. Right? This is just differentiation of L with respect to the second argument. Okay? So don't be put off by the fact that I'm differentiating with respect to derivative. I don't. I just take this function, and what this means, this is a partial derivative. What this means is I differentiate with respect to the first argument. That function L with respect to first argument. Okay? So my function, then what is written here is a differential equation for function f. And it also must satisfy our boundary conditions, and the function which satisfies this equation and the given boundary conditions will provide me with the minimum of this function. So again, the only thing which I need to know is this function L, which is here. And then I can immediately write, and if my functional has this form, then if I know this L, then I can immediately write what is the functional which provides me, what is the function, differential equation for the function which provides me with the minimum of my function. Okay? Any questions? No questions because you haven't understood anything, or no questions because everything is so clear that it just, what kind of questions can be?
So this seems like a really complicated way to explain a simple idea, doesn't it? I mean, it's just the idea is you've drawn your function over on the left or on the right, and you say we want to find where the minimum is, and all this you've done is just mathematical proof of how to find that minimum, right?
Yes. Yeah.
Okay.
Yeah. So it's not a proof. There is something more if you want to consider it as a proof, mathematical proof. But what I'm saying is that if you know functional, it means that you know the function L. You can write this equation right away, and the solution of this equation will provide you with the minimum of this function. Well, actually, it will provide you with extremum, but it usually is minimum. Okay. So let me do it real quick for the functional which we just discussed, the length. So what we have there for the length is that function L of the first argument z1 and the second argument z2 equals equals square root of 1 plus z1 squared. Right? Remember, that's length of my path. So now I take this. Remember that this is just differentiation with respect to the first argument. This is first argument is z1, so I need to differentiate with respect to this. So then this one instead of this one, what I have is 2. If I differentiate with respect to the first argument, I have z1 divided by 1 plus z1 squared square root, right? It's differentiation with respect to the first argument of this function. Just a derivative. Now, what it says is that after I take this derivative with respect to first argument, I need to put, instead of the first argument, f prime. So I do that. F prime of x, and here I have f prime of x. So this is this part. Now I need to take the full derivative with respect to x. d over dx, right? And now, so that's the left-hand side of my equation. Now I need to have the right-hand side of this equation. I take this function, and I need to differentiate it with respect to z2, the second argument. I look here, there is no z2 here, right? So it means the derivative equals 0. It doesn't depend on z2. So this is the equation for my f prime of x. See that what I need to do now, I need to take this integral with respect to x, so I need to differentiate f, so it will be f double prime here and so forth. And I need to take this derivative, and then I will have some nonlinear differential equation, which solution of which will provide me with the minimum distance between 2 points. All right? That makes sense?
Yes.
All right.
Yes.
So, what does it have to do with mechanics? I'm sorry, I need to go a little bit over time. So with mechanics, it has to do with on the following way. Let's imagine, so there is a Hamilton principle, which tells you, which is formulated like that. There exists a functional for any system. There exists a functional which is at minimum on the trajectories, true trajectories of our system. For any conservative system, so we constrain ourselves only with conservative system. So what it means is that functional is called action. So the statement is that there exists a functional which is called action such that, let's say that I want to describe my motion. Let's imagine that it's one-dimensional motion, but it works for any dimensionality. So this is the trajectory, right? Then that's a functional. There exists such a functional. Then it is minimum on the true trajectory, right? So if I take any function x of t whatsoever, all of them, and I compute the value of that action on those functionals, on those functions, and then I choose the function which provides me with the minimum of that action, then that function which provides me with the minimum will be the true trajectory of my system. And that functional, remember that every functional is given by some function L. That function L is called, in this case, is called Lagrangian. And it's given by a very simple story. It's that Lagrangian of x dot and x, right? It's instead of derivative with respect to x, I have derivative with respect to time, equals to kinetic energy of my system minus potential energy. So if I have this Lagrangian, this function L, I stick it here. Then I will have a functional. Then this functional is called action. And by the way, I integrate it with respect to t. So that action of x of t equals integral that L of function of x dot and x, the whole function of t time dt from t1 to t2. Initial final. So Lagrangian, and now if I take all the function x of t, all the possible trajectories, I stick them here. I compute them for all possible functions x of t. I stick them in all of them inside here. Compute that number which resulted, and I choose such a function which provides me with the minimum of the action. Then it turns out that it will be the true trajectory of my system in this potential field. Okay. So that's a Hamilton principle. And so again, you can do that. You can actually prove that on your own. So let's do that. I mean, sorry, it will take one more minute. So let's use our equation for the minimum. It's actually called Euler-Lagrange equation. And so what we need to do is we need to take L and differentiate with respect to the first argument. The first argument is only here. So when we differentiate L with respect to the first argument, what we have is m x dot. Right? This is the first argument. And we differentiate with respect to it. It's an argument squared. So that's what we have. Now we have d over dt, right? And it must be equal to the derivative of this function with respect to the second argument. The second argument is only here. X dot is my first argument. X is in the second argument. So you have minus du over dx. Right? If mass does not depend on time, then what I have here is just mx double dot, two derivatives over time, equals force. It's a Newton's equation. Okay. So it turns out that that's another reformulation of the Newtonian equation, Newtonian mechanics. It tells you that all you need to consider is that functional, that Lagrange. You write for any system, you write Lagrangian, which is kinetic energy minus potential energy for any system, and then you write Euler-Lagrange equation for that Lagrangian, which is just d over dt dl over dx dot equals dl over dx, right? And you're done. You have the equation of motion, right? It seems like overkill when you're talking about one-dimensional motion, but that x doesn't have to be one-dimensional parameter. It can be multi-dimensional parameter. Moreover, because the value of the integral, you can always inside this integral change the integration, which means the reparameterization of your motion. You actually are not constrained to any sort of coordinates. You can use any set of numbers as your coordinates, whatever you fancy. And it will still be exactly the same equation for any set of coordinates. And this is a very powerful tool because it tells you that, first of all, you never deal with vectors. You only need to write the functional, that function, which is Lagrangian, which is a scalar function. And you can choose whatever coordinates you want. You don't need to do the tricks to translate vectors from one set of coordinates to another. You just take any set of numbers which uniquely defines your system and use it as x coordinates. And after, and you write that it's just kinetic energy minus potential energy for that set of coordinates. And then you just write the equations, that Euler-Lagrange equation for each coordinate, and you're done. All the equations of motion are done. All right? That may seem like a complicated way of doing it, but in reality, as I said, I teach that analytical mechanics in undergraduate and graduate classes, and when students get to learn how to actually do that, the procedure of what you do it, they're so delighted because it's so much easier than trying to write all the forces acting on all pieces of your complicated system. You just write the kinetic energy, write potential energy, bam, done. All the equations of motion are here. Right? You really have to appreciate. You really start to appreciate the technique when you actually do solve the problems with that. Right now, for you, it may be a little bit overkill. It looks like overkill, but it's not. It really is amazing to do that. Now, for the last statement which I want you to think about a very strange idea which is here, and that idea is actually very important for the like modern physics. You see that what I just told you, that there is a functional which is called action, right? And the trajectory provides you with the minimum of the functional, right? But how does the system know that it should go in such a way as to provide a minimum of some strange functional? Now, you can think about it just to say that, well, this is mathematical curiosity, it just happens so, right? And you just figure it out that it's sort of another reformulation of Newton's law and be done with it. But usually when you have such a beautiful reformulation, and this reformulation is very beautiful when you start working with that, it means that there might be some deeper reason for that. And that deeper reason, to figure out that deeper reason, is exactly what moved the physics of like kind of leaps and bounds beyond what we knew before. So it's the idea that in order to find the minimum of the functional, you need to check all possible paths, right? So for all the paths, you need to compute this functional and then see which one provides you the minimum. So it looks like that if you take a particle, it should travel on the all possible paths simultaneously, and then take the memory of the functional, compute the functional on all the paths, and then compare them at the end, and then present you as if it just traveled on one path. Okay. Quite interestingly, that's exactly one of the reformulations, what I just said, exactly one of the reformulations of the quantum mechanics, which was developed by Richard Feynman, and not that long ago. It was, I think, 50s or 40s last century. And it was a completely new way of thinking about quantum mechanics, which allowed us to do a lot more in quantum field theory, because without that Feynman techniques, or we call them Feynman diagrams, no calculations is possible in field theory. That's, well, there are some exceptions, but there's a few. That's a major tool basically to figure out. But that's exactly what is happening. That hidden picture there is that the system should walk on all possible paths. All right. And it is not just a mathematical curiosity, it is really so. And we'll talk about it later when we'll talk about quantum mechanics. All right, that's it for today. And by the way, I know that it was over your heads, a lot of things which I said, but it's okay. That's designed this way. It's modern physics, right? You don't expect to understand everything, which people spent 100 years understanding. All right, any questions?
Yes, I had one question.
Sure, go ahead.
So for the L x dot x that you have on the board, it's m over 2 x dot squared minus u of x. Should that be a minus or should it be a plus?
It's kinetic energy minus potential energy.
Okay.
Right? So it's all Lagrangian is not energy. It has